In Chapter 8, we're going to switch gears and start to focus on the concept of probability. A probability experiment is a process that leads to well-defined results, which we refer to as outcomes. An outcome is the result of a single trial of a probability experiment. For example, we could look at the probability experiment of flipping a coin. One particular outcome associated to this experiment would be that of observing a heads on a single flip. One of the things we can do is find probability and think of it as a percent chance. When we flip a coin, what's the percent chance that it will land up on heads? And what's the probability? So whenever we're going to construct a probability, and we'll talk about this here in a minute, but the probability of getting, let's say, a head is going to be the number of heads that would be on a coin, which is 1, out of the total number of possible outcomes, which is going to be 2. We know that the fraction 1/2 would have a value of 0.5, and this would be the probability. So the probability of a head is going to be 0.5, and probabilities are always going to be numbers. They're going to be between 0 and 1. So anytime we compute a probability, it's going to be between 0 and 1. A lot of times people necessarily don't understand decimals, but it's a little bit easier to think of in terms of percent chance, where all you would do is change that decimal to a percent by sliding it 2 places to the right, and that would give us a 50% chance. So this is percent chance, but the actual probability would be the decimal value 0.5. A very important concept is that of the sample space. A sample space is the set of all possible outcomes of a probability experiment. For example, if we flip a coin 1 time, the different outcomes that we could observe would be either a head or a tail, so our sample space is head and tail. Notice that it is a set, so we're using the set notation where we have braces, and the individual outcomes are separated by commas. If we roll a standard 6-sided die, the numbers that show up could be anything from 1 through 6. And so our sample space here would be the outcomes 1, 2, 3, 4, 5, 6. In answering a true and false question, the 2 possible outcomes would be true or false. Again, writing it as a set. And if we flip 2 coins, our sample space would include these observations. It could be the case that both coins show a head, so that'd be head, head. Or it could be the case that both coins show tail. We would call that tail, tail. Another potential outcome could be that the first coin shows a head and the second coin shows a tail. We would write that as head, tail. Or it could be the first coin was a tail and the second coin would be a head. So when we flip 2 coins, this is our sample space, and it consists of these 4 outcomes. We now come to an event. An event is any subset of the sample space. A common example that will be used whenever we talk about probabilities will be to pull a card from like a deck of cards. The way that a standard card deck is constructed is there's 52 cards, and those cards are broken down into what we call 2 colors. There's half the deck is black cards, and half the deck would be red cards. Within each color, the deck is further broken down into what we call suits. The 2 black suits would be clubs and spades. The 2 red suits are going to be hearts and diamonds. Within each suit, there is the ace card, and then the numbers 2 through 10. And then we have what are referred to as the 3 face cards, which are literally cards that have faces on them, which would be the jack, the queen, and the king. And there's 13 of each suit. So again, half the deck, half of 26, or excuse me, half of 52 is 26. So there's 26 red, 26 black, and then each of the 2 suits is further broken down into half of the 26, which would be 13. So there's 13 clubs, 13 spades, hearts, and diamonds. An event within the deck of cards could be that of drawing an ace. That would just be a subset, which would consist of these 4 outcomes. So the event of drawing an ace would include the ace of diamonds, the ace of hearts, the ace of spades, and the ace of clubs. This now brings us to the theoretical model for probability. Let's suppose that we have let E be an event that is a subset of the sample space S. We will use the notation N of E to represent the number of outcomes in event E, and N of S will represent the number of outcomes in our sample space. The probability of an event E is simply going to be the number of outcomes in E divided by the total number of outcomes in the sample space. So you take the number of ways your event can occur, divided by the total number of outcomes in the sample space, and that gives us the probability of event E. This particular model for probability is under the assumption that we have equally likely outcomes, which is very important. So this would apply to things like random number pulling, drawing cards from a deck at random, or even like rolling dice or flipping coins. Suppose we roll a single die. We want to calculate the probability of each of these events, and then we want to put them in order of least likely to most likely. The probability of getting a 5 would be the number of 5s on the die. There's only one 5 out of 6 total number of possibilities. This would be 0.16 repeating, which I will round to 0.17. A number less than 5. So on the die, how many numbers would be less than 5? Well, we'd have what? 1, 2, 3, and 4. So that's 4 outcomes out of 6, which would be 0.67. And then the probability of an odd number, an odd would include the outcomes a 1, a 3, and a 5. That's 3 out of 6 possibilities, which would have probability of 0.5. At the end of the day, what we're measuring here is the likelihood of these events occurring. The one with the smallest probability would be getting a 5. So 5 would be the least likely event. The next one would be getting an odd, because that has probability 0.5. And then the one with the largest probability, which would be the most likely to occur, would be a number less than 5. And this is the kind of use that we get out of probability. A lot of times when we know that an event is not guaranteed to happen, we would like to ask the question, well, what are the odds, or what is the probability that that event may occur? And that's what the probability gives us a measurement of. Let's take a look at example 3. Suppose that 2 coins are flipped. Let's find the probability of getting 2 heads. So if you recall, the sample space for this event included head, head, tail, 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 head, and head, tail. So the probability of getting 2 heads, that happens 1 out of 4. So this would be the probability of 0.25. If we want to compute the probability of at least 1 head, at least 1 means 1 or more. That would include these 3 outcomes. So from the sample space, these 3 outcomes include at least 1 head. So that would have probability 3 out of 4, which would be 0.75. If we said at most 1 head, so at most 1 would mean 1 or less. Let me maybe draw this one in green. Which one of these have at most 1 head? Well, the first one wouldn't work because that has 2 heads. The 2 tails would actually work because at most 1 head would allow us to have 0 heads as a possibility. This one also only has 1 head. And this last one also only has 1 head as well. So from our sample space, we have 3 outcomes, which have at most 1 head. So that also would have probability 3 out of 4, or 0.75. A couple general facts about probability is that, first of all, probability will never be negative. Okay? So anytime we compute a probability, it always has to be either 0 or bigger. And furthermore, it can never be greater than 1. So anytime we compute a probability, probabilities will always have values that are in between 0 and 1. In the types of probabilities that we will compute within our class, which come from what we call finite sample spaces, getting a probability of 0 means that an event is certain to not occur. So if an event has probability 0, that means that the event cannot occur. Conversely, if an event has a probability of 1, those are going to be events that are certain to occur. So kind of at the extremes of our measuring stick of probability, we have events that would have a probability of 0. Those are going to be our impossible events. For instance, if I roll a 6-sided die and I ask what is the question that I roll the number 8, well, that's going to have probability 0 because there are no 8s on the 6-sided die. If I ask the question, though, what is the probability that if I roll a die, I get a number less than 10, that's going to be an event that's going to have probability 1 because all 6 out of 6 sides are less than 10. So that's going to be an event that's going to be absolutely certain or guaranteed to occur. So at the extremes of our probability ruler, if you will, we have events with 0, which are impossible events. We have things which are probability 1, which are absolutely certain guarantees to occur. Smack dab in the middle, we have things that are kind of like our coin flips, like flipping a coin and getting a head. These have probability 0.5 or 50% chance. That means that you would be as likely to see those events occur as what you would be to see those events not occur. For things that have probability between 0 and 0.5, we refer to these as unlikely events. And they're referred to as unlikely because they would happen less often than what they would actually occur. And things that have better than a 50-50 chance, we refer to those as likely events. Because on a single trial, those events would be more likely to occur than what they would be to not occur. Another fundamental property of probabilities is that if you add up the probabilities for all of the events in the sample space, it has to add up to exactly 1. We also have the notion of the complement of an event. So suppose we have an event E, which we previously defined as just some subset of the sample space. E complement is the event that E does not occur. So for example, if I'm looking at just a very easy example of a coin, if my event E is that of getting a tail, then E complement would technically be the event of not a tail, which for us we know would be a head. So E complement is the not E event. For example, if I look at, let me give you another example of a complement. If I roll a die, let's suppose that event E would be that of rolling a 1 or a 2. In that situation, E complement would be not a 1 or a 2. And then we can reword that a little bit differently. If I roll a die and I do not get a 1 or a 2, that's equivalent to saying that it must have been either a 3, a 4, a 5, or a 6. An easy way, if you have a sample space, okay, an easy way to construct the complement would be to do the following. So if my event E consists of the outcomes 1 and 2, if you remove those two, and so if you get rid of those two, then whatever would be left over within the sample space, that's going to be your complement. And the relationship between the probability of the complement and the probability of the original event is the probability of the complement of E is simply going to be 1 minus the probability of E. Let's take a look at the next example. They say, of the next 32 trials in a county court, 5 are homicides, 12 are drug offenses, 6 are assaults, and 9 are property crimes. If jurors are assigned to trials at random, what's the probability that a juror won't get a homicide case? So we're going to do this two different ways. We're going to compute this in the traditional sense, and then we're going to try to compute it using the rule of the complement. So if they do not get a homicide case, then that meant that it must have been one of the other offenses. So it could have been a drug offense, an assault, or a property crime. That's 12 plus 6 plus 9 different outcomes. So 6 plus 9 plus 12. If we divide that by the total number of possibilities, and they said that there was 32, this would give us the probability of not a homicide. Right? Because according to the definition, it's just the number of non-homicides divided by the size of the sample space. So 6 plus 9 plus 12, that's going to be 27 over 32, which would have a probability, just the two places, I'll call it 0.84. Another and faster approach would be to say, okay, if we want the probability of not a homicide, according to the rule of the complement, this would be 1 minus the probability of getting selected for a homicide case. This would be 1 minus, what's the probability of a homicide? Well, if we go back, there was 5 of those. So the probability somebody did get assigned to a homicide case would be 5 out of 32. So this is going to be 1 minus 5 out of 32 is going to be 0.16. And that also gives us a probability of 0.84. So we had two different approaches here in order to compute the probability of not getting on a homicide case. The idea here, and the reason why the rule of the complement, hopefully everybody sees this as being faster, is that the complement event can happen in so many different ways compared to the original event itself. So it's actually easier just to count the homicide cases, do that probability and subtract it from 1, than to have to break it down and to go into all of the individual cases that would be a part of that not complement event. So here's an illustration of that complement rule at work. The last model of probability that we're going to investigate is what's referred to as the empirical probability model. And this is when we have about events that are not equally likely and are based upon frequencies. You would use this kind of approach if you wanted to calculate the probability of rain on a given day at a set location, or if you wanted to compute the probability of there being an auto accident on a road, you would use the empirical model. The probability of an event in the empirical approach is computed by calculating the number of observed frequencies for an event. We call that F, and dividing it by the total number of observations or the total number of trials, which we will call N. For example, let's suppose that we're looking at people that have a certain blood type. We collect a sample of 500 people, and we see that 200 have type O, 223 had type A, 51 had type B, and 16 had type AB blood. What is the probability that a randomly selected patient has type B blood? Let's compute that. So the probability of getting someone with type B blood is the number of people that had type B, that's going to be 51, divided by the total number of people altogether, that's going to be 500, if we plug that in, 51 divided by 500 would give us a probability to two decimal places of about 0.10. If we wanted the probability of not B, the easiest way to find this is using the rule of the complement. We could just use 1 minus the probability of B that we got from above. This would be 1 minus 0.10, which would give us a probability of 0.90. In part C, it says, if a person with blood type A gets a transfusion, what's the probability that the donor had type O? I'm going to skip this one because it adds a little bit more to the table than what we're going to study in our class. In order to get transfusions, you'd have to know a little bit more about blood types, because there's certain blood types that can only receive from other types. So this question gets a little bit more involved than what we're going to study, and it actually would require some additional knowledge on transfusion. However, we can do the last part. Let's focus on this one. What is the probability that somebody had either type A or type AB blood? Okay. We know that there's 500 people altogether, and so we would just need to know, well, how many people had A or AB? There was 223 that had type A, and there was 16 people that had type AB blood. So it's going to be the 223 for the type A plus the 16 for type AB, which would give us 239 out of 500, which would be a probability to two decimal places. It would round to 0.48. So that would have a probability of 0.48.